All right, so today I'm going to tell you about a technology that's been developed. I have to stay here. I'm used to wandering. A technology that's been developed at UCSB and JPL with mostly NASA funding. It's a collaborative effort. Can I go forward with this? Okay, there we go. It's mostly a collaborative effort between my group at UCSB, where I'm a professor in the physics department. I have 6 graduate students and a couple postdocs. Here we are at the telescope. We also have JPL, which makes our devices, and we have teams at Oxford and Fermilab who are building instruments based on our technology. So the name of our technology is called a microwave kinetic inductance detector. It is a NASA-funded detector, which we'll go into the details of how it works on the next slides. But it's a superconducting detector technology with operating temperatures below 1 Kelvin. So these, the semiconductor detectors we've heard about so far are limited by the fact that they work through the photoelectric effect. A photon comes in, it knocks an electron out, you get essentially one free charge carrier. In a superconductor, the gap energy of the superconductor is about 10,000 times lower. It's like it's 0.1 millielectron volts instead of 1 electron volt. So when every photon comes in, you don't get one free carrier, you get 5 or 10,000. And that enables a quantitatively new regime where you can do much more than you can with a semiconductor detector. So what we can do is we can make single photon counting optical, near infrared, and all the way up to X-ray, including the UV, detectors with microsecond time resolution. So we can count when every photon comes in to a microsecond or better. And we can also resolve the energy of every photon. So when a photon comes in, we absorb it, and we can tell you its energy to roughly 10% in the current generation detectors. We have no read noise or dark current. These detectors, it's very hard to deposit between 1 and 4 EV of energy into a given pixel without being a photon. So for instance, a cosmic ray will light up our whole array, and we can do a time veto. So we can nearly perfectly eliminate cosmic rays, and we have no equivalent to read noise or dark current. And these are scalable to large arrays. We think megapixel scale arrays are doable. I have to get used to this time delay between hitting the button. Okay, so pixel for pixel, MKIDs are the most capable UV-OIR detector available. And I will take any arguments on that rather bold statement, but I think it's true. And hopefully we'll show it to you here. So the next slide. So this is the MKID equivalent circuit. What an MKID really is, at its most fundamental, is an LC oscillator tuned to work in the 4 to 8 gigahertz range. That's where the microwave comes from. It refers to the readout frequency of the detector. So that detector, so this little LC oscillator right here has an inductor and a capacitor. So what this does is give you essentially a little notch filter, and this capacitor couples it into the environment. So the net effect is that you have a photo variable inductor, and if we can go to I don't know if it's very slow. Okay, so here is, so the point, what we do is we make this little LC oscillator out of a superconductor. And so we can make a very high Q resonant circuit with loss Qs on the order of over 1 million. But we use a coupling capacitor to strongly couple with the environment to give us a resonator Q of about 25,000. And then when a photon hits the inductor, it causes the inductance to change through a phenomenon called the kinetic inductance effect. And this change in inductance is measured by sending a microwave probe signal through the device, past the device. On resonance, most of the power gets transmitted back gets reflected. But when a photon comes in, it changes the inductance, and then the microwave probe signal can pass back. So what we see if we look at the power transmitted past the device as a function of frequency is a little dip that looks like a notch filter. And this is at base temperature. The dotted line is at an elevated temperature, which is the equivalent of a photon breaking the Cooper pairs in the superconductor. So there's a phase and amplitude change that are related to the energy of the photon. So when that photon comes in and hits this inductor, what you get is a We sit around at some baseline value of the phase of this transmitted signal, and a photon comes in and we see a quick change and then a decay back to our baseline on a time scale of roughly 50 microseconds, which is defined by the material parameters. So what we can do here is we can measure the arrival time of this photon by where the pulse came in, and we can measure the energy of the photon by essentially measuring the pulse height. A blue photon will give a big pulse. A red photon will give a small pulse. So we have intrinsic energy resolution on every photon. And the key point about the MKIDs is that unlike some of the other superconducting detector technologies that have been around for 15 or 20 years, MKIDs are extremely easy to multiplex. So each resonator has its own intrinsic resonant frequency, and then we can tune each detector to have a slightly different frequency in lithography. You can think about this as pipes in a pipe organ. Each one has its own specific length, which gives it its own resonant frequency. So they don't interfere with each other. So what we can do is send a comb of frequencies in that we generate in our room temperature electronics, one probe tone in the comb for every pixel in our detector, and then we use some sophisticated room temperature electronics to read out that ensemble of tones, and that lets us do this, find the arrival time and the energy of every photon that hits the array. The nice thing is that working at these gigahertz frequencies, we can multiplex something like we currently do 2,000 pixels per wire. Going down to the focal plane. And this is what's going to let us hit these megapixel scales with this type of array. When we put these, well, what we can do here is, for instance, put in lasers at multiple wavelengths to calibrate the device. So this isn't one of our highest energy resolution devices, but here we're putting in a laser at 4,000, 7,000, and 9,000 angstroms. Each one each laser gives you a monochromatic response. So you can see this broadband photo absorption with energy resolution across a wide range of energies. So this is what our MKID pixel looks like. And we can show that there's a correspondence between this device and the resonant circuit. So the first thing you'll see as we go through this is that we have a coupling capacitor. So we have a microwave feed line which brings our signal down to our device. And then that signal, there's a parallel plate coupling capacitor which determines how strongly the resonator interacts with the environment. Finally, there's this large interdigitated capacitor here. That's the capacitor here. That's large to reduce one of the noise sources in our system. And we also have the inductive section, which is right here. This inductive section is the place that we're photosensitive. You'll notice that that's not covering a ton of, that inductor is not covering a ton of real estate on the detector. So what we do is we use a square microlens array, which has something like a 92% effective optical fill factor. And we concentrate the light down into a small spot on this pixel. And that gives us that effectively very high fill factor. The plate scale here is about 200 microns per pixel. That's sort of our comfortable range. Anywhere between 1 and 300 is a very natural scale. So these pixels are large, but that actually works well with the large telescopes that we're working on. It actually makes the optics for the cameras significantly easier than with the small pixels on conventional CCDs. So here's an example of one of our arrays. This is a 2,000 pixel array. This is not 2,000 by 2,000. It's 44 by 46 pixels, so 2,000 pixels. It has 2 microwave feed lines. And you can see that as we zoom into the array, this is where we bring the microwave signal in, and then there's this microwave transmission line that snakes back and forth. Every pixel has a slightly different capacitor to give it its own resonant frequency. There's a lot of fabrication effort and trial and error has gone into the microwave design of this device. We have, for instance, this is a bare silicon right here, the darker color. This is the niobium, which forms our ground plane. Then we have the tinitride film of the MKID, which is sort of a golden color. And then we have these gold bond pads. There's also SiO2 crossovers here to to get a good ground plane. So there's been a lot of work and a lot of trial and error that's gone into designing this array because there's really nothing like it out there. And this is one of our individual pixel designs. So we've now graduated on to a 10,000 pixel array design. This has 5 feed lines and will be used in several instruments that we have been funded to construct in our lab. So we've been funded by the NSF to build an instrument called Darkness at Palomar, which is used for coronagraphic planet finding, which Seth is going to talk about in the second half of the talk. We've been funded by the Japanese to build an instrument called MEC, which is a clone of Darkness for the Skexeo coronagraph at Subaru. This is another planet finder. And finally, we were funded recently by NASA to build the imager for the Picture C balloon. So these will be going on a balloon in around 2019. So here is just an example of some of the data we took with the MKIDS. This was taken at the Palomar 200-inch telescope. We did pointings on a 6x6 grid and imaged ARP-147, which is an interacting galaxy. Up here you see the HST image, so we're not going to do as well as them because we have the atmosphere in the way. But we can see that we're recovering most of the gross features like this, nucleus being offset and this arm, the spiral arm here puffing out, and this dust lane right here. But we made all the colors with this, not through narrowband filters, but just using the built-in spectroscopy that the MKIDS provide. So we've made a lot of progress, a lot of it in the last couple years, going from not having a functioning detector technology to now having an instrument deployed for 34 observing nights and science papers published on observations from the detectors. And now we've been funded to build 3 new instruments that promise even more impressive results. I'm calling the technology level 3 to 4. If you were talking about for ground-based instruments, it would probably be TRL-7. But for space applications, it's probably TRL 3. So we've been thinking hard about using these in space, and one of the ideas we had was we proposed to this SALSO concept about a year ago to use the second NRO optic. And the idea was to combine 2 technologies to greatly enhance what you can do. And so we combined our MKID technology with a solar electric propulsion system to put us into an orbit that gets outside the zodiacal dust background. By combining those 2 effects, we could effectively increase our sensitivity to something like 500 times greater than HST with the same size optic. This is a really impressive improvement. This technology was going to requires both our MKIDS to be functional, but also the solar electric propulsion to put it in an orbit past Mars. So this was a cross-cutting technology that took in quite a bit of technology, both from astrophysics and from planetary science and from the human side for the solar electric propulsion. So this is just a slide showing some of the things that this faux mission would be able to accomplish. But I'm going to move on to this last slide, and that is that there are a significant number of other potential applications. MKIDS really excel when every photon matters, and they're useful for things like satellite-based reconnaissance, X-ray beamline studies, semiconductor process debugging, laser communications and quantum key distribution, as well as biological fret imaging, anything where you have a hard time turning up your light source. For instance, on the beamline, if you turn, we make X-ray versions too. So these are all applications that that really are interesting and cutting edge and difficult to do with MKIDS. So I'll turn it over to Seth to talk about the other applications.
All right, thank you, Ben. So obviously there are many very exciting applications for MKIDS across many fields, but especially in astrophysics. I'm going to talk about the one that we're most interested in, that is very applicable to NASA specifically, and that we are focusing on the most right now in our lab, and that's the direct imaging of exoplanets. So this image that I'm showing here was not taken with MKIDS. This is one of the earliest directly imaged planet systems, HR 8799. You can see the central star here has been masked out to reveal 4 faint companions orbiting around it. And the interesting thing about this image is that it's still fairly representative of the current state of this field. So all of these planets are kind of 5 to 10 Jupiter mass in size, and they're orbiting at a distance outside of the orbit of Saturn around our star. So there's still a lot of room for technology to continue improving this field. You know, this is from 2010, so it's a little old now, but all ground-based surveys that are going on now are still kind of looking at systems in this scale, so large planets that are fairly far out. And as the technology progresses, it'll continue to push in to look for planets closer to the host star and down to fainter and fainter targets. So with all this headroom for new technology, there's a lot of space for MKIDS to really have a major impact. And this has recently been recognized in the 2013 NASA Astrophysics roadmap, where they were called out as a potentially game-changing capability. And that's what I'm going to try and convince you of today. So first, I need to talk about the current major limitations to doing these kinds of observations. And to do that, I need to start with introducing how they're made. Luckily, chronographs were introduced earlier today, so I can breeze through this slide pretty easily. You start here at the end, where you collect the light in your telescope pupil. You focus it down with a lens to create an image of your star, which you can then block out with some kind of opaque mask, just a black spot in this simplest schematic. You recollimate the beam with the lens to go back to your pupil plane, where you see the residual diffracted light that has gone around your occulting spot, which you can then block out with a secondary stop. So when you form your final image, you've now blocked out a significant fraction of the light, down to 10, to the scale where you want to be able to image Earth. So you need something like 10 billion contrast to get to those levels. So, but of course, these simulations are all shown with perfect optics in a perfect world. And in reality, there's aberrations on all of these optics and on these masks, and from your wavefront incoming. So instead of a nice image, what you get is this characteristic speckle pattern from the scattered light that gets outside of your control region. And the extra annoying thing about this speckle pattern is that it changes with the different wavelengths that you look at it, and it also changes in time. But it not only changes in time, different speckles can change on different timescales. Some are very slow, relatively static, and others can change on timescales less than a second. But the most problematic ones are ones that have coherence times of about 1 second. So these are too slow to let them average away with long integrations, but they're too fast to control with current detector technology that you would use for your science camera. So to track and correct these speckles as completely as possible, what you really need is a detector in your science plane with energy resolution, some photon counting or very high time resolution, and no extra dark current or read noise. And of course, these are all the key characteristics of MKIDS that Ben just introduced earlier. So we've been funded to build several instruments to try and demonstrate the potential of using MKIDS to do this very difficult measurement. The first of which is known as darkness. It's a 10,000 pixel array, which is being built for integration at the Palomar Observatory behind the Project 1640 chronograph and behind the upcoming Stellar Double chronograph. It'll operate at wavelengths slightly bluer than most current direct imaging surveys. And it's designed as just a drop-in replacement for the current imaging camera that they're using behind those chronographs. So darkness exists in the lab, as you can see here. It's undergoing final integration, getting ready for its first cool down and device testing. And we expect to be on Sky with it in about a year to really start taking data and testing the performance. So once we're on Sky, how do we expect it to do? This plot is showing the typical figure of merit for these types of instruments, which is on the y-axis the contrast that you can achieve, plotted in these units as the planet brightness over the star brightness. So lower down, bigger negative numbers is better contrast. And you want to know how you're going to do as a function of how far away from the host star you're looking. So this black curve is the simulated performance behind Project 1640, just the raw chronographic performance that they can get with their current chronograph architecture. And this green curve is the performance the simulated performance of 1640 after the post-processing that's available to them now. And this curve actually matches very well with their current on-sky performance. In their recent paper where they published the first results, these 4 planets here are the 4 HR8799 planets that I showed in the image earlier. And they were able to recover the B and C, but not quite get down to D and E in J-band, which is this plot. And as this has already popped up, you can see the punchline that with the post-processing that we can apply with MKIDs, we expect to be able to do a factor of 100 better. There it is. So that's very exciting. We should be able to push down to contrasts that are not really achievable with any other ground-based exoplanet imaging survey right now. Also very interesting, this plot on the left is showing the same kind of curves, but in I-band, slightly bluer wavelengths, where these planets actually have not been detected yet, as far as I know. Someone should correct me if they have when I wasn't watching. So these points are taken from atmospheric models and estimated contrasts. And we see that if Project 1640 was sensitive down to these wavelengths, they would not be able to recover it. But with darkness, we think that we will be able to. So we'll be able to start putting new data points on constraining atmospheric models for these large exoplanets. Next. So around the time that darkness is finishing its construction and getting commissioned on the telescope, we'll also be starting work on a new camera for an instrument called Picture-C, which is a NASA-funded balloon-based instrument that will utilize the Wallops arc-second pointing gondola for balloon missions developed by NASA. And it will integrate a back-end chronograph. Behind the telescope isn't shown here, so this is just a preliminary schematic of the chronograph that it will fly, and an MKID camera, which is scheduled for flight in 2019. It's actually a 2-phase flight where the first one will just demonstrate some of the optics and pointing technology, and then the second flight will actually integrate the vector vortex chronograph and the MKID camera. So the science objectives for this mission are very similar to other current missions, to image exoplanets and disks around other stars. But what's especially exciting for us is the technology objectives, which is to flight demonstrate MKIDs for the first time. So this is a direct stepping stone for us by 2019 to flight test MKIDs and bring their TRL closer to a point where we think we can put them in space. Next. Because of course in space is where the ultimate exciting result will be found, which is to look for Earth analogs. The search for other Earths is laid out in the NASA Strategic Plan objectives, just shown here, to understand the evolution of our solar system and look for the potential for life on other planets around other stars. And we think that with the game-changing capabilities that MKIDs could bring to a space-based Earth imaging mission, that they could really be an enabling technology to make it possible to do this kind of very difficult characterization and measurement. So that is where we're going. This is the current status of the technology, just to summarize. The technology is functional and producing science on ground-based telescopes now. There are 3 new MKID instruments in development, including one to demonstrate it as a flight instrument on a balloon. But the MKID arrays are still very far away from their ultimate potential. There's still a lot of room to improve the energy resolution and array size and yield. So the exact numbers to advance this technology will depend on the application, how big of an array you need, what wavelengths you want to work at, how much we'll have to move away from the wavelengths that we're used to working at. But the kind of 10 to 20,000 pixel planet finding instruments that we showed here are all ready now for about $1 million each. So as Ben said, and you can argue with him about this, this makes MKIDs currently one of the most powerful and capable detector technologies available. Of course, the major setback is that they're superconducting, so maybe not setback, but the trade-off is that they require very low temperatures. However, for applications on the ground where the added cost is modest, the performance improvements that they offer far outweigh that. And you have to remember that in space, current and future X-ray and far infrared missions will all require similar cooling capabilities, and many of them already do. So there's a lot of synergy there with piggybacking on that development to get MKIDs into space as well. And I think that that's it. So here's some contact information and references to the papers, and we'll take questions.
You can take the plan if any questions.
All right.
But you don't have to come back. It might be for you.
These are exciting, the MKIDs. I've been reading about them for years, and it's exciting that you've got 3 instruments demonstrating them with light on the sky. Question is about your cooling. Are you currently using just helium cooling, or are you looking at other cryocoolers and then looking to see, do you have any concerns whether moving to that approach will cause drifts or other issues, noise?
Sure. Yeah, we're building, the darkness instrument is going to use a liquid helium cooler, and the mech instrument is using a pulse tube cooler, in which our first prototype instrument, Archon's, also used a mechanical pulse tube cooler. So those both technologies work fine, and it's just a matter of size, packaging, and cost. We prefer the pulse tube coolers because you don't have to pay for the liquid helium. So I definitely prefer the mechanical coolers, and they both work fine. To go from, that gets you down to 3 or 4 Kelvin. To get down to our operating temperature at 100 millikelvin, we use an adiabatic demagnetization refrigerator. It's a magnetic refrigerator that will get you down in a single shot or in a multi-stage method where you can stay cold if you have 2 of them. And it's a very robust technology. It's actually TRL-9, having flown on Astro E2. So actually Goddard will sell you that component, the ADR, off the shelf, basically. So actually the hard part is getting to 3 Kelvin, not getting down from 3 Kelvin. And that, there's multiple ways to do it. I mean, the JWST Miri cooler would do it, for instance, but it costs too much money. So I think that's one of the things that STMD is actually working on, is these space cryogenics, and we'll benefit directly from that. So most of the chain is TRL-9 already.
Yeah, so what's your baseline cooling for the Picture C? For the
It's going to be liquid helium because it's only an overnight flight.
Yeah, okay.
So we have we actually have another balloon concept, Echo, that's gone in last year and will go in again this year, that has the capability to do like a 50-day long super pressure balloon flight using like a 250-liter giant storage door of liquid helium and flow through cooling. So that's possible because you have to weigh the power requirements of running the cooler versus the liquid helium cost. But it's doable. Thanks.
You mentioned a little bit about the insensitivity to cosmic rays. Can you explain a little bit more about what you meant, why it's insensitive?
Yeah, so this is an interesting thing, and I do think the MKIDs, we haven't tested it yet, but they should be extremely radiation hard because we make them out of a titanium nitride ceramic, which is a tool steel coating on a sapphire wafer or a silicon wafer, and we don't rely on the anything semiconducting to make this work. So they should be very rad hard. But what happens is, a typical cosmic ray might be a radioactive decay or a muon. It usually deposits energy in the crystal, and that energy is usually way more than an optical photon. It might be an MeV. And what happens is the energy comes out in a phonon shower, and the whole crystal kind of lights up with these phonons bouncing around, and then those bounce into other detectors nearby. So when you have a particle event, it lights up all the pixels at the same time. And so we search in 10 microsecond bins for coincidences. So if we have more than about 10 events across the array in one 10 microsecond bin, it's a cosmic ray. And we throw out the time interval around that cosmic ray. And it means that we basically throw out on the ground something like 0.01% of our exposure time. but essentially perfectly veto cosmic rays. So that is actually an important point for something like TPF or one of these, any space mission where you have to do essentially a long exposure, like you would with a conventional detector on a terrestrial planet finder mission. You're going to be getting bombarded by cosmic rays, and you're not going to be able to read out your detector fast enough because you have to get above the read noise in this very dark environment. And the MKIDs will basically solve that problem right away. That's an additional advantage.
You might have said it, I might have missed it. Does the MKIDs have any sort of crosstalk electronics issues that are inherent to the design, or it actually does better than the conventional infrared detectors?
Yeah, we don't see, we haven't tested to the level that like the Hawaii 2 detectors for the near infrared have been tested. So but we don't expect there to be anything equivalent to charge persistence, for instance. There could be thermal crosstalk between detectors, which won't cause you any false signals, but could slightly degrade the energy resolution that you see. We haven't seen that yet, and I don't think it's going to be an issue at the energy resolution of 20 to 50 where we think we're going to be. If we eventually push to R of 100 or 400 sort of towards the theoretical limits at these low temperatures, then we may see more sort of thermal crosstalk issues. The electrical issues are possible, but we can filter a lot of that in our digital electronics, and we haven't had any problems. Occasionally, if we have two resonators too close to each other, we'll lose one of the pixels, and that gives us limited yield, so we have some dead pixels in our array. It's one of the things we need to fix. But that usually just kills a pixel and doesn't give you false counts.